Some might say that mining is an important feature of Minecraft. The ability to place new blocks is of course also essential. Let me show you how I implemented both of these into my custom server written entirely in Rust. It also almost broke me. Anyways, let's dive in. Mining blocks is the first thing we will look at, simply because it's the easier feature to implement. The client informs the server that it broke a block by sending a player action packet. This packet is used for multiple things at once, but for our purposes it is very simple to pick apart. The first field is the status. This can be one of multiple values. For digging in creative mode it will always be a 0. Next comes the location. These are the coordinates of the block that was just mined. The phase isn't really relevant for us here. This would tell us which side of the block was hit. The last value is a sequence counter. This is a unique number that the client assigned to this operation. Once the server received and understood this packet, it will respond with the acknowledge block change packet. That also contains the same sequence ID. Now the block will have disappeared and appeared again for the player. This is because the client shows a block in the way it thinks it will be broken or placed, but once it received the acknowledge block change packet, it will fall back to the information that the server provided. So let's provide this information. This happens in the form of the block update packet. This packet needs to be sent by the server to all clients that have the chunk loaded. It contains the location of the changed block and the block ID. We will get into this later when we take a look at placing blocks. For now a 0 is sufficient, as that stands for air. It is of course impossible to destroy a block, you can only replace a block with air. Now let's take a look at placing blocks. This will be a little bit more complicated, so we should start simple. For now, let's not worry about which block to place, just where to place it. The client will inform the server that it just placed a block with the use item on packet. It starts off with the hand. It's a 0 for the main hand and a 1 for the offhand. You may already start to see why this gets a little bit more complicated. Next is the location of the placed block. Just as with the player action packet, we also have the phase that the block was placed against. Now there are 3 floating point numbers for the cursor position. This is where the player looked when they placed the block within the block that they targeted. We will briefly come back to this later when we will take a look at slabs. Inside block is just a boolean that's true when the player's head was inside a block. This is apparently used for properly implementing scaffolding. After that, there is another boolean that is always false according to the wiki. It should have something to do with the world border. And last but not least, we have this sequence counter. This is exactly the same as in the player action packet from the previous section of this video. This is all the information the server is going to get to determine which block got placed where. For now, let's just pretend it was stone and move on. Well, before we can move on, we need to send an acknowledge block change packet back to the player that sent the use item on packet. Also, you guessed it, we also need to send a block update packet to all players that are in range. We will also soon need to actually deal with the location field of the use item on packet. So I created a position struct in my library to work with positions as they are defined in the protocol. A single 64-bit value is used to store a position when it goes over the network, which is pretty compact. It does mean that we need to do some unpacking, however, if we want to get the individual coordinates out of this big number. The first 26 bits are the x coordinate. This is followed by another 26 bits as the z coordinate. The last 12 bits are then used for the y coordinate. We are actually getting kinda close to the 30 million blocks that the world extends for in each direction. 26 bits gives us roughly 33.5 million blocks in each direction. The code for encoding and decoding positions looks a bit funny if you don't deal with bitwise operations often. First, let's look at how to get a position from raw ones and zeros. We can use the function for getting longs from a byte vector as a starting point. To get x, we just need to shift all the bits right by 38 bits. For y, we instead shift left first by 52 bits. Now we just have bits of y left over, so we can shift back to the right by 52 bits again. You can probably guess how we get at the z coordinate. Correct, we shift left by 26 bits and then back to the right by 38 bits. This was still simple compared to turning a position into bytes. For this we need to first truncate all the coordinates, just in case they might be too big to fit in our custom length integers. To do this, we do a bitwise AND on the coordinates and 26 1-bits for the x and z coordinates and 12 1-bits for y. Now we just need to shift x and z over. As the last step, we just do a bitwise OR on all the individual parts. Phew, that was a lot of bit math for one video. So let's quickly jump over to the next section before my f***ing head explodes. To figure out which block the player is trying to place, the server has to keep track of players' inventories. As you might have already noticed, inventories are made up of multiple slots. Each slot can then of course hold 0 or more instances of the same item. Let's take a look at how Minecraft stores these individual slots. It starts off with the number of items. If this is a 0, then that's it. Very space efficient. If it's more than 0, then things are getting a bit more complicated. The ID of the item needs to get stored here, of course. The rest is then dedicated to components. I haven't yet looked too closely at them, but they seem to be there for giving items their behaviors. The max stack size component, for example, would tell you the max stack size of the item. In our slot data structure, we have to specify which components we want to add and which we want to remove. Why is removing components necessary? According to the wiki, this can be used to remove the default components from an item. You want uneatable bread? This is probably the way to do it. Okay, let's see how this component stuff gets represented in a slot. First, there are the number of components to add, and then the number to remove. These are classic varins. Then we have the actual arrays of components. These get referred to here by their numerical type. For the components to add array, we also have to specify the value. This differs between the different types of components. For the max stack size component I talked about earlier, this value is a varint. Some others are a lot more complex though. There are 95 different types of components at the time of making this video, which is a lot. Coding all of this up has been a bit of a chore, and I even left out the really complex ones for now. If only we had a data structure that was purpose-built for holding arbitrary data. What? As far as I could find out, NBT was actually used for this before version 1.21. Madness! Now that we have the basic building blocks of inventories implemented, let's draw the rest of the owl. To do this, I added an inventories field to my player struct. Its type is simply a vector of slots. I also added a number to keep track of the slot in the hotbar that the player has currently selected. This alone doesn't do a whole lot. We need to listen to the set creative mode slot packet that the client will send to the server each time the player acquires an item from the creative inventory. This packet just contains two values, the number of the affected slot and the item. Each slot in the player's inventory has a number assigned to it, as you can see here. The item is represented as a slot. That's why I spent a whole last section showing you how they work. As the player is currently only able to be in creative mode, because I haven't implemented game mode switching yet, handling just this packet is fine for now. Then there's also the set held item packet that the client sends to the server each time the player switches the selected hotbar slot. This packet is even simpler. It only contains a single number with the ID of the newly selected slot, ranging from 0 to 8. We just laid all the groundwork to know which item the player held in its hand when the client sent a use item on packet. The item alone is not really useful, however. We need something called a block state ID. We already used two in this video, 0 for air and 1 for stone. These are very simple blocks, so let's take a look at some wooden logs instead. They exist in 3 different states, one for each orientation. In the case of oak logs, if they are oriented along the x-axis, they have the ID 136. 137 is for oak logs oriented along the y-axis. This is also the default. Each block has one default state, which will become useful later on. ID 138 is then obviously reserved for oak logs oriented along their z-axis. Things only get more complicated from here, with blocks like doors having many more block states. One for each unique combination of where they're facing, if it's the upper or lower half of the door, on which side the hinge is, if it's open, and also if it's powered. Doors aren't even the most complicated blocks. At least each block has a sensible default we can fall back to for now. Then we can implement proper logic for choosing the right block state in the right situation later on. At first I started with just some manual mappings of item IDs to block state IDs. After I had confirmed that my assumptions about all of this were correct, I could move on to set up some data structures to hold items as well as blocks with their different states. The item struct is still very bare bones because all I actually need here is the name and ID of the item. This name is then the same as the block's name. Speaking of blocks, they have a type which will become important later on when I implement proper state choosing. A type might be slab, stair or door. Logs are rotated pillars. Next, there are the properties. These represent all the possibilities for modifying the states of blocks. These states are then stored in a vector. Each state has its unique ID, a boolean that tells us whether it's a default, and again a vector of properties. Each element in this array then has a unique combination of properties. This isn't really enforced through the type system, but it's fine, I swear. Also, yes, I could have put the default in a block struct itself, but for now this is all fine. Now that we know the block, we have to choose the right state. For now, I just take whatever the default is. In short, we start from the inventory vector stored in the player struct. Then we look into the slot that was active when the client sent the use item on packet, get the item's ID, convert that to the item's name, get the block with the same name, and then get the right block state ID from its state vector based on what the default state is. Sounds complicated, but manageable. With all the data structures in place and some manually added data, it was time to implement the block state choosing code for logs. To my surprise, I got this working fairly quickly. We just look at whether the block we got back has a property for X or Z. If it does, we check the phase it was placed against. For the x-axis, we check if the phase was either 4 or 5, and if it is, we get the block state ID associated with it. This is all just very basic and not scalable to all properties for all types of blocks. Well then, let's make it scalable to all properties for all types of blocks. I only implemented a couple of items and blocks by hand for testing, as doing them all by hand would take me ages. Luckily, there's a better way. If you run a Minecraft server in this special way, it will spit out a bunch of JSON files that contain lots of interesting data. I'm only interested in 3 of them for now: the blocks, items, and registry reports. For example, this is how an oak log looks like in the block report. The type, properties, and states are all in here. The same goes for the item report, where an oak log looks like this. In here there are no item IDs, however. These, of course, are pretty important because those are stored in the slots in the inventory. These ID to name mappings are contained in the registries report. It contains protocol IDs for more than just items. Searching for oak log here reveals that they have an ID of 49. This is of course very different from the block state IDs. To generate all the code to represent all items and blocks, I started a new binary crate. It contains just a single source code file that has functions for all the individual things I want to generate. Then I just uncomment whatever function I want to run. It's quick and dirty, but it works. This file does contain some real programming horrors, so let's not look too closely at it. In the end, it just prints out all the code to the console so that I can copy and paste it into my editor. Again, quick and dirty. I could have probably written some macros to generate this stuff at compile time, but that would also require access to the JSON files we obtained earlier. I'm not sure if it's cool to just upload those to GitHub, so I'd rather not. The items were relatively simple, but the block states turned out to be a bit more complicated. The problem is just that there are a ton of properties that also carry different values depending on the type of block. I ended up generating a ton of enums for each property and block type combination. There are also a ton of block types, 267 to be precise. I also wrote a function to generate the enum for those as well. For storing all the items and blocks, I created a hash map with the name as the key, and then the block or item struct I showed earlier as data. But now I should be able to place any block I want and at least get the default state. Well, it wasn't quite that easy. I just ran into a new problem for the first time. I just blew up the stack. That's right, calling the function to get the hash map with all the blocks used more stack memory than is available by default. Manually raising this limit actually worked, and I could verify that my code was doing its job correctly. But I also knew that I had to reduce the amount of stack memory used. I tried a few different approaches, but in the end I had to split up my 30,000 line function into many smaller functions. Instead of building the hash map in one shot, I now have one function per block that adds all the data for this block to the hash map. This also had the benefit of reducing compile times a little bit. It still wasn't great, so I moved all the generated code to its own library crate. Because this won't change often, it can just be compiled once and then stay cached. With this, compile times are back to normal for small changes in the main library or server binary. Players can now place and break blocks and also see blocks broken and placed by others. But when a player leaves and rejoins, they just see an empty world again. That's because the server doesn't actually keep track of changes made to the world yet. Fixing this, of course, required some new data structures. It all starts with a world that contains a hash map for all the dimensions. Each dimension in turn contains a vector of chunks. Each chunk then stores its chunk coordinates as well as a vector of its individual sections. Each section then contains a vector of block state IDs. These are ordered in the same way as they are in the chunk data and update light packet, going up by the x coordinate first, then by z, and finally by y. I then added some utility functions. Dimensions now let you get a chunk that's located at either a chunk or block position. You can also override any block by just handing this function a position and block set ID. Getting blocks is also easy with this function that only requires a position. Chunks also have a function to get and set blocks. Here the math of converting between position and indices in the blocks vector of the chunk sections is handled. Yeah, let's not look too closely at this because I barely understand it myself. But hey, it's working. To keep track of the state of the world, I also added a world property to the central game object. Now I just had to replace a bunch of code in my packet handlers to update the world whenever players change some blocks. Also, when joining, players now get served the world as it is stored in the game object, instead of whatever we generated before. After fixing some bugs that were caused by my poor understanding of simple mathematical concepts, this worked perfectly fine and it was time to move on. All the bones are now in place to implement the logic to always get the right block state when placing down a new block. It will probably be a little while until I actually did all of that work, but for now I wanted to start with some common blocks that are also complex enough to be interesting. But before I could get started on that, I needed to move this code out of the handler and into my library, where I started a new block state module for this. The logic for choosing the right block state is different for each type of block, so I started out with a match on the block type I got back from my function that turns the held item name into a block. The first type I added was for rotated pillars. These are of course the locks I had already managed to implement earlier. With the new structure, this code looks a lot more clean already. Next, I tried doors. They are very complicated as I had already teased earlier. For starters, when you place down a door, two blocks are actually created: the bottom and top part of the door. I wasn't quite sure how to best handle this, but I came up with a fairly clean solution, I think. I just changed the return type of my function to be a vector, so that it can specify multiple blocks and their positions in the world. Next was the direction of the door. This depends on the way the player is looking, which I do already keep track of. The problem was just converting this angle to a cardinal direction. It took me a little bit to figure this out with some trial and error. Then I realized that the angle can also be negative. I should probably look further into this at some point, but for now it's fine, I guess. Well, and then there are double doors. This necessitated checking an adjacent block to see if there's already a fitting door there. If there is, then the hinge of this new door has to go on the other side. Then I thought to myself, okay, now things can only get simpler. Boy, was I ever wrong about that one. Let's talk about slabs. At first it seems easy. Just check if the slab was placed on top or underneath another block, or if the cursor was on the upper or lower half of a block. Then there are also double slabs, of course. So now I also gotta check if there already is a slab there that can be turned into a double slab. But placing a slab underneath a lower slab shouldn't turn that slab into a double slab. It took me a while to figure all these edge cases out, which was kinda frustrating. Then I also wanted to do stairs. I already knew that all the curved stair logic was not gonna happen for now, so I just focused on their orientation and whether they are upside down or not. This reduced stair feature set was then pretty straightforward to implement. I will probably do some more block types from time to time in the future without talking about it much in my videos, but for now, that's it. And with that, let's see all of this in action. Welcome back everybody to another episode of Let's Play Minecraft here today with me, TXT, and...
Me, not TXT.
Perfect. Go.
I can join the server? Or will it break?
Yeah, of course. No, it will not break. What do you think of my programming abilities?
So I'm already on... Ah, there you are. Perfect.
Oh, hello.
Let me have a good look at you. Can you turn your head? No? Okay.
Fix that one, but I mean, you can try maybe breaking a block or something.
Yeah.
Oh yeah, I can also see what you're doing. That's
Oh, that's interesting. You can break blocks, but your arms don't move when you do that. That looks really strange.
Yeah, there's still maybe a little bit of something missing for that.
See something.
Maybe you want to start building something interesting.
Yeah.
Do you have any ideas in mind?
Yeah, I definitely need a starter base
Yeah, so Mr. Block there, by the way. Just
Huh?
just so you know.
No, I did not.
There's a block missing here. Is there not?
That's on you. You
No.
just have to imagine it. Okay, so now we need a door. I know the doors are trouble, but I will try. Ha. Now can I
Why
open
would
it?
doors be trouble?
Oh.
I mean, that is not implemented yet. Now I'm in a bit of a predicament.
I thought you did all that. I thought the doors are implemented.
Placing doors, right? But breaking doors also.
Oh,
not.
now there's half a door. Okay. Yeah, I see.
Yeah, this is peak software development. I don't know what you mean.
I thought we can build a house now.
We can.
Can I
just can't
get
open the
through?
door.
Okay, yeah. Oh, the glass is also behaving in weird ways.
No, that's just a vanilla experience. That's how it's supposed to look like. Wonderful, perfect. How about a nice roof for this beautiful house?
Yeah.
Maybe let's go with birch pressure plates.
You do that side of the roof and I do this side.
Diamond blocks, how unoriginal. You really gotta
been done
embrace the difference with the Oxide server by being able to just use alternative blocks for alternative uses.
Are you sure this is structurally sound?
Yes, of course.
Okay, good. So
You just
not
have
gonna
to
dig in.
look from the right angle, of course, you know.
I mean, I can't even stand on it. Don't think that's a problem for a roof? I mean, I guess I don't need to stand on the roof. I can just stand on the floor.
If you look from the
So
right
you
angle,
got a
it
point.
almost looks like it's solid, you know.
Oh,
Okay,
can't
but how about
spawn
an actual
animals.
roof with actual stairs, maybe?
I just noticed they changed all the icons of the eggs, the spawn eggs.
Or can you make stairs out of granite and stuff now? What happened? Are we playing a mod pack here, or what's going on?
I don't know what you installed. Bamboo stairs?
What the heck is a resin brick?
Bamboo stairs. That's incredible.
What is this?
Resin brick? What? There's resin?
It also sounds really weird.
I think I'm allergic to all these new additions.
Look,
Okay,
I just make a Minecraft server, right? I have no idea about any of the game.
About the game. Okay. Yeah, I can't test out the anvils. I can't use them. They're hanging signs.
Oh my god, what is this?
It's a hanging sign. This is amazing.
God.
Goat horn.
Oh my god, you can now in creative mode, you can get like the different paintings directly as an item. Did you break my beautiful server again? Yeah, I think you've broken it. I will need to restart the server.
So is our stuff gonna be lost or will it still be there?
Yeah, this is sadly going to be lost.
Oh no. All our progress.
Yeah, this is truly one of the saddest things that have ever been experienced by humans. I mean, we have built the dirt house now, right? So now the next step in a normal Minecraft career is, of course, what are you doing there? That seems pretty illegal.
This is perfectly normal behavior.
Ha! Trapped you.
Shit, I can't open it. I'm forever trapped. Okay, yeah, it's definitely an interesting door. And trapdoors, can I place those?
Oh, you can also replace blocks. Can you hold on for a second?
Hold on to
Stop
what?
it. Can you
What?
stop moving around?
What do you mean? What should I hold?
You should just hold your horses, okay?
Oh. It's pretty dark.
inside of the diamond cube. I think this is truly a work of art. It really says something about society, I think.
Oh, that is interesting. I can place the glowstone like where I'm standing. That shouldn't work.
And you can try building up like that. That's a really interesting challenge.
Mm-hmm. Oh, it pushes you away. Okay. If you just...
So slime blocks actually do their thing,
That's
interestingly enough.
Nice, okay.
So that means that slime blocks are implemented on the client side.
Yeah.
Okay, so do you maybe want to clean up a little bit before we leave this world behind? Wonderful.
Okay, all tidied up.
Yeah, I guess then
Ready for the next update.
we can leave the server again and then come back another time when there's stuff to try out again. So back to the main video, I guess. Yeah. Bye. That was a lot of progress for just one video, wasn't it? This really starts to feel like Minecraft now. Next time, I'm probably going to implement chat and commands, depending on how complex that will end up being. You should probably subscribe if you don't want to miss that. See you then.